record. I forgot to send out a Canvas announcement, but again, the office hours are, the TA office hours is going to be today at 7 p.m. and then another one tomorrow at 3 p.m. this time, basically. I'm going to have my office hours at 3 p.m. or sorry, right after class on Wednesday. Okay. If not, I'll go ahead and get into the lecture content. Just one last sound check. Everyone in the room here can hear me, obviously. All the people on Zoom can hear me well. All the people on Zoom can, I think I'm sharing my screen right now, if I'm not mistaken, right? And you guys can see me do that. Cool. Awesome. I'm really excited to get this going. So we spent the past couple lectures last week talking all about vectors and tensors and stuff like that, right? And so now we're going to get into more than just vectors and tensors, but also like vector and tensor calculus. Okay. And so the first concept we're going to need to talk about when it comes to vector calculus is something called field. Okay. And fields are actually, it sounds kind of complicated, but in the context of this class, it's actually pretty simple. It's basically just any variable defined as a function of position. And that position is obviously, x1, x2, and x3. And of course, we can think about position as a vector as well, right? Because it also has 3 components. Okay. And so you guys have almost certainly played with fields before. You can think about like a concentration field if we're talking about mass transfer, or heat transfer, you can think about a temperature field, right? And then of course there's also vector fields where like, that's a lot of the things that we're going to be dealing with in this class. You could imagine that something like this could be a velocity field or something, right? The position itself is also a field, right? A position vector can also be a field. So for instance, like if the origin is right here, just making sure I'm visible, if the origin is right here, and then I can think about like any position in space can be thought about as a vector connecting the origin to where I happen to be. Okay, and you can do basically any of the operations that I'm going to talk about today, you can also do with the position vector field. Okay, when we start doing calculus, we care a lot about, or we'll use something called the del operator a lot. Okay, and so that's defined as this. Okay. Sorry, these are unit vectors, so that's a vector right there. And of course, we spent all of last week talking about index notation, and so we're not going to forget all of that. In shorthand, this is just written like this. And it's an operator, but it basically works just like a vector. Okay, and then all the different operations that we'll do when it comes to vector calculus and stuff will basically involve this sort of, will involve this del operator. For instance, you guys have almost certainly seen a lot of these already. There's something called a gradient. Okay, now in the context of vectors and tensors is what we've talked about in the past week. A gradient is defined as a dyadic product of del with a field. Okay. Now that's a complicated way of saying, remember the dyadic product is when you just take 2 things and smush them together, right? So the dyadic product of like 2 vectors A and B was just AB, and that gave you a tensor, right? Because each of those vectors is, you could think about it as like a 1-dimensional or something like that, and then you smush them together, you get something 2-dimensional. Okay. So for instance, a gradient of a scalar looks like this. Dyadic product of that with some sort of scalar. And so then it's basically just, you guys can see my cursor here, both at home and in person, right? And so it's basically just this smushed together with F. Okay, and the result is a vector. As we're familiar with. Okay. If I haven't convinced you that that is a vector, then again, you can apply the rules of index notation, and you will find that it is, in fact, a vector. You can also do a gradient of a vector. This is maybe something that you have not done in previous classes, right? But you can take a dyadic product of basically anything with anything, right? Maybe one of the things that we were able to convince you of in the lecture on Friday was that you can do dot products and cross products and everything with tensors, just like vectors. You can do them with even higher order tensors and all of that fun stuff, right? So the gradient of a vector just looks like this. And so this is the dyadic product of del and v. And so it looks something like this. Okay? And this result is a tensor. Okay? This is called the velocity gradient tensor. We'll use this all the time. Right? You can imagine reasons why in a fluid mechanics class we would use this all the time. Okay? Writing out the matrix component of that tensor would then look something like this. And et cetera. As you can expect, there are 9 components to the tensor. It's a tensor, right? I could also have written it out lengthwise. That would just be dv1, dx1, e1, e1, dv1, dx2, e1, e2, et cetera, et cetera, et cetera, right? Okay, that's actually fairly simple. Let me just go ahead and bang out some of the other things that you can do with del. You can take a dot product of del. So this is the gradient is a dyadic product of del with a field. You can also take a dot product of del with a field. And that is something called the divergence. Perhaps some of you guys have seen this before as well. This is del dotted with a field. Okay. Now in this case, it doesn't make sense to dot anything that's not a vector or above, right? And so del dot v is then, well, the definition of del is that, or the definition of a dot product is delta ij times the first thing I, the next thing j, right? So that would be like that. Sorry. Right? But we often just do a shorthand and write that, right? Again, it doesn't make sense to do like a divergence of a field of a scalar field, but you can also do a tensor field. Okay. Pay attention to the order of the operations here of the indices, right? This is tau ij, and we're dotting it. The dot product is in front, and so we're dotting it like this. It's the I down here, right? If this were tau transpose, then it would be tau ji, and then we would be like taking the gradient of the second index. Okay. If you're confused about how that works, then write out the components of this. So this would be tau ij times ei ej, and then we're dotting that with this guy up here. And so the ei dots with the first thing, with the first index, right? Okay. We can also do a curl. That's del cross a field. I can write field, okay? And we have already defined what a curl is, and so let me just go ahead and talk about that. Or we have defined what a cross product is. That's just epsilon ijk. And now it's del cross that, and so the first thing is this. That's the first index, and then the next index is this. Right? And of course, we're used to thinking about curls in terms of a determinant, and so we can basically do that. This is basically the cross product. That looks like this. Okay, that's the definition of the curl. And then the last operation that we'll talk about in this class is the Laplacian. Okay. And as you guys know, whoops, whoa. That's del dot del. Okay, or another way of writing it is del squared. So it's the dot product, or it's the divergence of a gradient. Okay. And that we can do to a scalar. It looks like that. Okay. In this class, I will write the Laplacian like this, not the other way that you guys might be familiar with, which is, you know, df dx squared, dx1 squared plus df d squared f dx1 dx2 squared and stuff like that, right? The reason is just because, as you guys know, in index notation, you sum over repeated indices. Okay, and so if I do the squared, then that just gets more confusing. Okay, so this way of writing it will hopefully be clear that, you know, if we actually wanted to figure out what this is, then we would have to sum over I, right? And as pretty apparent from here, what's implicit in this is that we're summing from I goes to 1 to 3, and so this equation is just equivalent, or this expression here is just equivalent to this. Like that, right? But you guys already knew that because of the rules of index notation. Okay. Now, of course, you can also do a Laplacian of a vector. Okay, and that works essentially analogously. Okay, and this Laplacian is basically just a vector. Okay. Again, here, implicit in this expression is an EJ unit vector, and then we're summing over both I and J. And you guys can write out what that sum would actually be. What you'll find is that it'll be basically this for V1 times E1, and then this for V2 times E2, and then this for V3 times E3. Okay. Any questions about these different operations? I think for a lot of you guys, this will basically just be review, right? You guys have seen what a divergence and a curl and a gradient is, right? Nod your heads both over Zoom and in person if that's really true. Good. And so hopefully I'm just giving you like a new twist on something that you guys already know. Okay. The nice thing about what we're able to do now with everything that we know is that there are times when we need to do pretty complicated operations with all of these different things. So for instance, as an example, let me try and prove this relationship, which we'll actually use later on in the class. Okay. This looks pretty complicated, right? And it gets really, really difficult to like keep track of what's actually what, right? If we didn't know what we already know, I'll show you guys that in index notation, this proof basically just takes like 2 lines. Okay. If we had not known index notation and we had not known all we know now about different vector manipulations and stuff, you guys would probably stare at that and be like, "Whoa, holy shit! How do we deal with this?" Right? In fact, how do we even really read this? Right? This is a gradient of a vector that's already a tensor, and so that's already a little weird, right? We don't know exactly what that means. Okay, so here's a tensor. Now we're going to take a transpose of that. Okay, that's even weirder, right? And then, okay, at least the least thing that we can do right here is just make sure that this equation even makes sense at all, right? So let's think about it, right? On this left-hand side, we have 2 tensors. Okay, good, we add them together, and then we dot that with a vector. And so then we should end up with a vector, because a vector dotted with a tensor is a vector, right? Kind of like how a vector dotted with a vector is a scalar, right? And so if you dot a vector and a tensor, then you get a vector, right? On the right-hand side here, what we have here is a gradient of a dot product, which is a scalar. right? And so that means this guy over here is also a vector. And this is a Laplacian, and the Laplacian of a vector is also just a vector, as we've seen over here, right? So at least that kind of makes sense, okay? Let me try and write down what all these things actually are in the next notation, okay? So del v, you could write that like that, right? dvj dxi, okay? And just to make sure there's absolutely no confusion, let me make sure my i's curl one way and my j's curl the other way, okay? Like that. Now, again, implicit in this expression right here is an EI and an EJ, right? So what this expression actually says, just write it out real quick, is this. And there are 9 terms of this expression, right? We wrote out that matrix somewhere up, like further up in the notes, right? Okay. Now, this guy transpose is basically just this, but with the indices switched around. Okay. Now you guys might think, wait, but this is really confusing, right? Because like, why did I decide that this is dvj dxi? I could have decided that this is dvi dxj, right? And instead I could have called this dvj dxi. That gets really confusing, right? But just write out the sums and you'll be able to figure it out, right? Because implicit in this expression is again sums of over I and j of whatever I have written here times EI, EJ. And hopefully you guys can see that these two expressions are different. Okay? And so these two things are not the same. For instance, let's say the 1, 2 component of this tensor, so where I is equal to 1 and j is equal to 2, this is dv2 dx1. This is dv1 dx2. Those two are different, right? Now in this particular case, it doesn't matter because we're adding these two things together. And so this guy right here is a symmetric tensor, right? And if any of you guys have started your homework, you guys have already started to play with what a symmetric tensor is and stuff like that. We talked briefly about this on Friday, right? Okay, let's press ahead in this proof then. Now, the left-hand side, let me just copy that over here. Okay, that's equal to the divergence of these two things added together. Okay, and so therefore, that looks like this. Okay. And well, we can basically just distribute that out, right? You know, the sum of a derivative is equal to the derivative of a sum, right? And so then the first term becomes okay, and the second term, oh, sorry, there's a d squared here. And the second term becomes this. Okay, note how on the bottom here, I could have written dxi, or I could have written dxj, dxi, it doesn't matter. Order of derivatives doesn't matter, right? That's still true in the next notation, that's true no matter what, okay? So now we can basically simplify this into non-next notation terms that we're quite familiar with, right? Does anyone know what this is? Unmute yourself and talk, or just everyone, or anyone in the class talk, and then I'll repeat what one of you said. Does anyone have any idea what this is?
Laplacian form of that one?
Say that again?
Is that the Laplacian?
That's the Laplacian of v, right? Of the vector v. That's exactly what we have right here, right? So the first term is, on the right-hand side, first term, is del squared v. Okay? Now the second term is a little more complicated, so we'll go through that together. This is like a double derivative. The indices are different, and so it looks a little strange. But check it out. I can rewrite this like this. Right? Like I said, I can switch the order derivatives, right? That's true in index notation, regardless. Okay? And so you guys can see what dvx, dvi, dxi is, right? Let's say someone in the room, does anyone know what that is? dvi, dxi? Yeah, that's just del dot v, right? So someone in the room said that's just del dot v, okay? And then when we take ddxj of that, that's a different index than before, and so that's del whatever was inside. And so this is sorry. Like that. And there we have it, right? That's exactly what we're trying to prove. This first term is del squared v, and the second term is del dot v. Is del dot v. Okay. Let me try something real quick.
Could you explain something real quick?
Yeah. Is that better lighting? Can you guys actually see me?
Yeah.
Over Zoom. And does that affect what people in the room can see up on the board? Good. Go ahead and ask. I think it was it Kevin?
Yeah.
Go ahead.
So when you applied the outer del symbol to the quantity on the left side.
Tell me
Right
when to
there.
stop. Right here.
Right there. Yep.
Okay.
Why do you use the index I instead of a new index like K or something?
Oh, yeah. I mean, I did kind of skip a step. This is actually right here. If I want to do it fully, I could do something like this. Like that. But it's a dot product, and so I can just use the Kronecker delta and then make it go away, right? If your question is why do I use ddxi and not ddxj, that's just by convention of how we apply dels to things. It's the same reason why, like up here, for instance, or up here when I take the gradient of something, or if I take the del dot something right here, I always do xi. Okay. If I wanted this instead to read if I wanted to do dxj, then I would take the transpose of the top and then reindex. Okay. Does that answer your question a little bit?
Yes. Thank you.
Awesome. Okay. So it's kind of cool, right? Now you guys can actually see how we could prove different things. I think there might be a few examples later on in the homework where you have to prove things like what is del cross something, or something like that. And you'll have to use like identities, you'll have to mess around with indices, and it'll be a lot of fun. It'll be incredibly confusing, but once you get it, it'll be a lot of fun. And of course, we're always here to help you guys figure out why you use certain indices and stuff like that. Okay? Now, of course, this is not just a math class. We're also talking about like actual fluid mechanics and stuff like that. And so let me actually get into a little bit of the physics of things. Again, this stuff might be a little bit of review to you, but maybe a more rigorous explanation of phenomena that you already know, okay? So we already defined what these different operations are, but I'm gonna spend the next half of the lecture actually explaining what these different relationships actually mean, okay? So the physical meaning of a gradient, the simplest thing to think about is a scalar field. So let's do that. We'll consider a scalar field. I'll call that psi, x1, x2, and x3, right? Another way of writing like psi of x1, x2, x3 is you could also write this as that, right? Again, position is also a vector, okay? So one thing that I'm going to ask then is if we're given the value of the field at any given position, Wow, that's written terribly. Let me try that again. The value of field at any given position. Then what is the value at a position pretty close by? Another way of writing this is, let me draw a little picture here. Here's the axes that we like to write. Okay, if I know the value of my field right here, okay, or another way of writing that is, again, I have a position vector x that connects the origin to the point that I care about. Then the question is, what is the value of my field right here at some small distance, delta x away? And then, of course, by definition, this vector right here is just x plus delta x. Okay. In this class, whenever we think about small deviations away from something, we think about Taylor expansions. Okay, we're talking about calculus here after all, right? And so let's go ahead and do that. Okay, so that means the value that we care about can be written in terms of what we already know, plus several derivatives, right? We have to do it in terms of x1, because you move some distance in x1, you move some distance in x2, and you also move some distance in x3. Okay, and then of course there are higher order things, but let's not worry about that at the moment. Okay. And so what that means then is if I'm going to move this guy over to the left side of the equation. So that means that the difference between the value of the field at those two locations can just be written in shorthand or in index notation like this. Right? Again, implied sum over repeated indices. So I'm summing from I going from 1, 2, and 3. That's what I have here, right? Or in non-index notation that perhaps we're still a little bit more familiar with at this point. It's the dot product of the gradient of psi and the delta x vector. Okay? And so what this means then is that if my gradient, which is the vector, is just pointing in any odd direction, okay, and that means for my field, then that means that if I'm moving in my field in whatever direction, if I happen to move in the same direction as the gradient, then this quantity right here, which is equal to the dot product of those two vectors, is going to be maximized. Okay, if I'm moving in the opposite direction, then the dot product is going to be minimized. And if I'm moving perpendicular to that, then the dot product is going to be 0. Right? So what that means then is that del psi is a vector pointing in the direction of maximum change in psi, right? And the magnitude of del psi is the amount of change. Okay. I think most of you guys nod your heads here and over Zoom know this definition of gradient, right? But I'm not sure if you guys have seen this sort of rigorous proof of why that actually is the case. Okay. We have a little bit more time. We can talk also about the physical meaning of divergence. Okay, remember with divergences, we have to deal with vector fields because it doesn't make sense to take a divergence of a scalar field. Okay, so let's now consider a vector field that looks like this. That. Okay, so here I'm going to have to draw a little bit more complicated of a picture. Here's again my 1, 2, and 3. We're going to think about a little box. Okay, that box is going to be centered around a point. So I'll say a box centered around some sort of point in space that we care about, where the field is evaluated. Okay, and we're also going to give this box a certain volume. So this length right here is delta x1. This length right here is delta x2, and this length right here is delta x3. Okay, and of course, it coincides with the axes of which they point. Okay, and the box is in 3 dimensions. So if the pen will let me, okay, that actually worked out pretty well. Then there's a back and a front and stuff like that as well. Okay, and so the divergence is going to be very related to a quantity that we care a lot about in fluids, and that's the flux in and out of this box. So that's the surface integral. That's the surface integral of the vector field dotted with the unit normal of this closed surface. Okay, so let me just make sure I annotate that correctly. So n is normal to S, and by convention, it always points outward. Okay. So we need to basically evaluate this quantity over all 6 faces of our cube. Let me just pick 2 of them real quick. Okay. I'll go ahead and just pick, let's say, this one. I'll call that the front. Okay, so the one that's closest to all of you guys. And then I'll do, later on, I will also do the one back here in the back. This is not the top. I'm trying to come at the back. Okay, so here, let me draw that a little better. It's going to be face B, and I'll call that the back. Okay. And so at face A, okay, the quantity that we want, or this integral, is going to be f dot n times the unit area here, ds, right? And that area is, well, that's just delta x2 times delta x3. Okay. And now we can figure that out, right? The value of the field at this face is equal to, well, f of x1, x2, x3, except this is at the center of the box. I care about what it is at the actual face, right? And so it's a value of x1 over 2 shifted forward. So that's f1 evaluated x1 plus x1 over 2, x2 and x3. And let's not forget our delta x2 and delta x3. Okay. And by Taylor expansion, we get that, whoops, no underline there. We get that plus it's actually delta x1 over 2. And of course, higher order stuff. Okay. And still delta x2, delta x3. Now, oh, one thing I should mention is this one thing that a step that I skipped here is this is actually f dot E1 times delta x2 delta x3, right? Because the unit normal at face A is the vector pointing in the one direction E1, right? And so that's why this quantity on the right-hand side here is F1, because f dot E1 is just F1, right? Let me try that a little bit better at the next face. At face B, okay, then again, we care about f dot n. It's a cube, so same area as before. Except in this case, we have f dot negative E1, because we're at the back face now. And the unit normal now points in the negative E1 direction, right? It points towards the back. Okay. Again, times delta x2 times delta x3. Now, f dot negative E1 is then, by definition, negative F1 evaluated at this location. Okay. Again, the box is centered at x1, x2, x3, but we care about stuff, but we need to slightly shift it by an x1 over 2. And so it's going to be evaluated here, right? And we can Taylor expand this now.
Wait, Mitchell, could you explain really quickly why are you shifting it over again?
Oh, because I'm dealing with a box here, right?
Right.
And the box has finite dimensions, x1, x2, and x3, right? And so if the scalar field, if the vector field is evaluated, or if the box is centered at x1, x2, x3, and I want to know what the value of the vector field is actually at the surface of the box and not in the middle, then I have to shift it by the size of the box divided by 2, right?
Okay.
If I have a box right here, and my vector field is a value has some value here, that's going to not necessarily be the same as the value over here. Okay, that makes any sense.
Yeah.
Yeah. So delta x1, delta x2, and delta x3 is small enough that hopefully that variation doesn't matter. But that's where the higher order terms would come in. But those decay fast enough that it doesn't, that shouldn't really affect this calculation. Okay. Taylor expansion. Sorry. One more technology thing. When someone in the room asks a question, I'm assuming the people in Zoom have no idea what was just asked, right? Okay, the question in the room that was asked was, does that mean now I'm assuming that the value of the vector field is constant over the whole face of the cube now, right? And the answer is yes, basically, I'm assuming that. I'm assuming that the cube is small enough that hopefully those variations don't really matter. And everything I'm going to deal with in the future is basically in the limit when x1, x2, and x3 go down to 0. And so then hopefully that doesn't matter. Okay. The problem is just that like this sort of like this separation, this gap here, actually does matter because that decreases at the same rate as something else in my limit. And I'll show you guys what I mean in a second. Okay, so Taylor expansion, again, right here. So here I have negative of f1 at x1, x2, x3. Now we have a minus df1, dx1. I can write it properly. Delta x dx1 over 2 plus et cetera. Like that. Okay. And now if I need to do my surface integral, remember I'm integrating over the surface right here, then that's going to be these two quantities added together in total over A and B, right? And so in total over A and B, okay. Well, then I just need to add these two things together, okay? Now what do I get when I add these two things together? This term is f1 at x1, x2, x3. This term is negative f1 at x1, x2, x3. And so that actually cancels out, right? So there's none of that. this term right here is positive df1 dx1 x1 over 2. And this term right here is negative that, so also positive df1 dx1 delta x1 over 2. So what I ought to get is that times x1, x2, x3. Okay, because the 1/2 plus 1/2 is equal to 1. Okay, and so I'm not going to do the other 4 faces of the cube. You guys will get really bored if I did that. What I'll just tell you is then that the total flux then looks like this. Sorry, that's an x1. And hopefully you'll believe me that the calculation is essentially the same over the other over the other 4 faces as well. Okay. So as I mentioned, I'm going to assume that that delta x1, delta x2, and delta x3 are really small. So I'll divide through by x1, x2, x3. Or the other way of thinking about this is delta v, right, the volume. And so what that means then is that, oh yeah, and then the other thing I should mention, you guys have probably already recognized this, but this here is the divergence, right? And so that means, therefore, del dot f that. Okay. You guys see where that came from? It's kind of cool, right? And so the last thing I'll get into today is a direct result of this, but not over really, really small areas, just over any sort of finite volume that I care about. Maybe something that you guys have seen already. This is called the divergence theorem. Okay. And that basically is just a rehash of this, but just not when delta v goes to 0. It's just over any finite volume. Okay. Is that the volume integral of the divergence is just equal to the surface area, or the flux, the surface area of the flux. Okay. And this is a theorem that we'll use throughout this class, especially towards the beginning when we start deriving all these different conservation laws and something like that. So this is for any arbitrary closed surface. Okay. Let's see, it's 3:47 right now. I have a whole other thing about physical meaning of the curl, but I'm going to have to do something that's roughly as long as this. And so let me just go ahead and stop here. While you guys are all here, though, and while you guys are all on the Zoom call, if there are any questions about anything, go ahead and bombard me. But just to give you a quick preview, over the next couple lectures, we're going to talk about curl, and then we'll actually start to talk about different conservation laws and how we are applying all this math to really understand the fundamental equations of how fluid mechanics works. Questions from anyone? Does this all kind of make sense?
The divergence of a tensor have any like easily explainable meaning, or like similar to the divergence of a vector?
No. So the question that was asked in the room was does the divergence of the tensor have any sort of easily explainable meaning, as we talked about here? And my answer is basically no. There's not an easily explainable meaning, but the divergence theorem still totally applies. And if you want an easily explainable meaning, in general, for all of these things, you can always just think about, well, a tensor is just a vector of vectors. And so you could think about it like a tensor is the one component of a tensor, or the first component of a tensor is a vector. And so you can think about applying the divergence theorem to that, and then applying it again to the second component, and applying again. So it's like 3 divergence theorems all smushed together, if you will. Okay, that's another way of thinking about the velocity gradient, for instance. Right. So here we did a physical meaning of the gradient. We talked about a scalar field. If instead we talk about, del v, right? Remember, as we showed up here, that's a tensor, and that's just really annoying to deal with. But instead, you can think about that as, okay, well, in my velocity gradient tensor, then I can then think about, del v vector that is a tensor quantity, right? The components of that tensor are individual vectors pointing in the direction of the maximum change in v1, v2, and v3, right? And so maybe that'll help it'll blow your mind for a second. But if you think about like stuff in terms of the individual components, then it actually makes sense. Okay. Any other questions from anyone in the room or anyone over Zoom? Yeah, in the back. Yeah, this, right? Oh, this. Okay, so the question was in this proof, basically, where did this term come from, right? And the reason is just because if you look at the second term right here, by definition, it's a second derivative of vi with xi and xj. And so a second derivative is I take a derivative once and I take another derivative, right? And as you know from elementary calculus, right, you can take those in whatever order that you want. And so if I instead decide to take the xi first, then dvi dxi is a dot product, right? Now you could do it the other way, but if you do it the other way, then it gets really confusing, and it should be the same as what we did, and so therefore we did it this way, basically. If you did do it the other way, then you would get a tensor, like your dvi dxj would be a tensor, it would have 9 components in there, and then you'd have to be really careful when you actually try and take like dxi of that, making sure that you're summing all correctly, either along the row or along the column and stuff like that. And so that's why it's just so much easier to do it the way that we did it in class. Okay. Any other questions? Otherwise, I'll see you guys on Wednesday. Okay. Remember where you're sitting. For the people that are in class, remember where you're sitting. Remember the rules for in-person is that you have a seat and you're supposed to sit in that same location throughout the whole term. Just so in case you guys want to here at the very end of class, what I'll do is, can you guys just in the classroom sit tight for just a quick second? I'm going to pan the camera out in case you guys want to just see what our classroom looks like. And I'll go ahead and stop share. Okay. So that's what our classroom actually looks like. That's roughly where everyone is. That's the overall capacity. Okay, it's a fun time in here. Okay, all right, thank you guys so much.